Okay, right, and I'm co-host, so, okay. All right, any questions from anybody? Otherwise, I think we have all the committee and he'll get here in a couple minutes.
Sounds good. Let me share my screen as I get ready for this. All right, and then whenever we're ready, we'll get started.
Okay. Yep, looks good. I see the slides. Okay, I think go ahead and get started because he should be here just any minute.
Sounds good.
Okay, thanks.
Awesome. So good morning or good evening, everyone, depending on where you are. Thank you all for being here. It's really good to see all of you. Today, I'd like to talk about the safety assurance of autonomous cyber physical systems, which is a title I use as a catch-all for the work I've been involved in over the last couple of years. A key idea here is that there's been a massive surge in machine learning and AI-based innovation, generating a lot of excitement around their applications. So over about the last decade, with steep advances in sensing technology and other hardware, there's been a real interest in using AI methods to lay the groundwork for the proliferation of a diverse set of semi and fully autonomous systems. And one such example is the growth of the autonomous vehicle industry, which according to McKinsey has seen over $330 billion invested into over 2,000 mobility companies since 2010. And while much of the technology within this space has moved forward expeditiously, formal safety assurances for these systems still lag behind. So building these systems is quite a complex endeavor, and it requires designing the system such that it can navigate in dynamic and uncertain environments. A task that often combines traditional programming with machine learning, since some actions are difficult to characterize explicitly, and they're more easily derived through data-driven procedures. So as an example, autonomous vehicles frequently leverage machine learning to semantically parse their environment and navigate appropriately. So unfortunately, as we've seen in recent years, some of the advantages of machine learning come at a cost of fragility. And what I mean by fragility is that these components can fail in unexpected ways. So in a famous study by Christian Szegedy and his colleagues, the authors demonstrated that by carefully applying small modifications to input images, you could cause these components to produce incorrect classifications. These inputs are known as adversarial examples, and their discovery has really caused concern over the safety, reliability, and security of these machine learning applications. But beyond adversarial examples, the number of edge cases that an autonomous system must be able to handle is quite large in practice. And despite our best efforts to estimate all the foreseeable scenarios that these systems must be able to deal with, we don't have any way of knowing that we've identified all the possible threats to, or even the failure modes of the system. And given the fragility of learning-enabled components, we'd like to have a principled way of identifying when the algorithms powering these systems are tasked with handling situations that they haven't been prepared for. And while the examples I've shown on the screen can be viewed as funny-looking glitches, the system's inability to figure out what's going on in the environment shows how astoundingly difficult it is to prepare these systems for the incredible range of edge cases that they may encounter in the real world. So as with most disruptive technologies, societal acceptance of autonomous systems hinges on an ability to engender trust in the underlying technology. And while there's been a lot of work in this space in recent years, there's still a mountain to climb with a steady drumbeat of new stories of AI failures that range from the trivial to the tragic. And rebuilding confidence in these systems will require holistic analyses of their design and their interactions with their world, particularly within the realm of safety. So one of the chief challenges in reasoning about the safety of these systems is while there are numerous established and historically effective methods for reasoning about the correctness of traditional systems, and by traditional systems here, I mean the systems that don't make use of machine learning, systems that have this data-driven nature are more challenging to deal with. And there are broadly two kinds of challenges. The first is the need for approaches that can handle the analysis of machine learning methods within these systems. And in this context, one of the fundamental challenges is that it's incredibly difficult to pen down a precise formal description of what the system is actually supposed to do. So instead, machine learning components are generated by training them on a large set of examples of the task that they're being required to learn, and then testing to see how well it learned that task. And while many forms of testing has led to the generation of these high performance systems, a lot of them are not sufficient to guarantee correct behavior in safety critical settings. And the second challenge is that currently most assurance approaches are predicated on the assumption that once the system is deployed, it doesn't learn and evolve, which might not necessarily be the case when you're considering the particular operation modes for an autonomous system. And finally, the safety assurance arguments that we develop for these systems must be able to deal with the reality that realizing autonomous technology involves a combination of a heterogeneous set of physical, networking, and software components, yielding systems with numerous interfaces and interrelations that require careful attention when we're reasoning about the behavior of these systems. And systems that exhibit these interactions are referred to as cyber-physical systems. And the underlying principle here is that the computational and the physical aspects of the system cannot be easily decoupled. So as an example, you can imagine then changing the rate at which software executes within a particular component in the systems will have consequences on the types of behaviors that it can enact. So the safety assurance question for cyber-physical systems here requires interdisciplinary efforts drawing from real-time systems, control systems, hardware design, and safety engineering as well. But even more important is how these systems are integrated to form a cohesive whole, which is itself a non-trivial problem. So to this end, the two research questions that I addressed in my PhD are: one, how do you develop safety assurance arguments for autonomous systems that operate within these dynamic and uncertain environments? And then two, how do you reason about safety when machine learning components are deployed within these systems? So much of the work I've been involved in draws on formal methods, which are a class of mathematical techniques used to specify what the system can or cannot do. And this framework is governed by the use of models or abstractions of the overall system that might include modeling its physical dynamics, as well as the underlying software. And using these models, you can perform these analyses of the behavior of the system and check if they satisfy a set of requirements that may be derived from industry standards and best practices. So if the system satisfies these requirements, then you can provide the artifacts that led to that conclusion. But if not, then the task is to obtain an example of incorrect behavior that can be used to refine its construction. So these analyses are often done at design time, since we want to ensure that the system is constructed properly from the beginning and avoid expensive, non-trivial changes that would be necessary if these analyses were done after the fact. However, we also need to perform such analyses online to make sure that our design assumptions are still valid at operation time. Since one of the fundamental challenges within this space is that at design time, we don't have any way of knowing that we've identified all the specific threats to or the failure modes of the system. So it's imperative to continually monitor the system as its objectives and environment evolve. So with that in mind, my work over the last couple of years can be divided into two camps. The first is the design of these runtime assurance techniques for components within autonomous systems. And the second camp is helping in the creation of the design time assurance techniques for machine learning components. Specifically in this case, we considered a class of machine learning models known as artificial neural networks, which have generated a significant amount of excitement over the last couple of years. And in this talk, I'm going to focus on the runtime assurance techniques that we've been developing and make use of a formal methods technique called reachability analysis. And this approach allows you to perform exhaustive, rigorous explorations of the system's behavior. Specifically, I'm going to focus on two projects that I've been working on over the last year within this realm. And the first project deals specifically with how reachability analysis can be used to reason about the safety of an autonomous system within the presence of uncertainty. And the second project deals with generating safe control systems within an autonomous racing context. So then I'll then conclude with a discussion of open research questions. So with that, let's get into the details. And in the first part of this talk, I'll be discussing my work on reachability-based safety assurance for autonomous systems within the context of uncertainty. I want to start first by introducing the three major building blocks of autonomous applications and highlight where machine learning components can assume a significant role. So the first major task is perception. So in order to successfully navigate through the world, the system must have a deep understanding of its environment and how this environment is evolving over time. And based on this understanding, the vehicle must then come up with a plan with how to move in this environment in order to accomplish its high-level goals. And then once a plan has been generated, the vehicle then needs to be able to generate the steering and throttle commands that allow this plan to be executed. And the interactions between these tasks determine the success of your system. So classically, machine learning has been used within the perception and the control stacks due to the inherent complexity of outlining the relevant operation zones where the vehicle can drive, classifying and tracking obstacles within the environment, and then even projecting how humans or other vehicles will move within this environment. And since manually coding up solutions to all the possible scenarios is infeasible, machine learning models is an attractive solution here. Since you can train these models to handle these tasks based on massive data sets of driving these vehicles in a variety of contexts. So now if we assume that we have some working model of the system, or we have some solution to the previous mentioned tasks, one of the things that we like to do is demonstrate that our implementation is robust and works well in practice. Moreover, one of the questions that we like to answer is what happens if the predictions that our machine learning components are making about the environment are wrong, and then lead the system to make a bad decision. In this case, what we'd like to be able to do is intervene whenever we think an errant decision has been made, so that our system remains safe at all times. And one of the ways this can be done is by forecasting the effects of the control decisions made by the components in your system to see, for example, if they ever lead to a potential collision. And if you can do this rigorously and effectively, then you have a robust way of arguing that your system operates correctly. So now one way of reasoning about the correctness of a system over a large set of scenarios is called reachability analysis. And one of the key benefits of reachability analysis is that if you have a realistic model of your system, then what you can do is forecast the evolution of the system over a finite time horizon that you're concerned about, and obtain the set of behaviors that your vehicle enacts. In this case, I'm referring to dynamical systems analysis, where you have some model of the physics of the vehicle that is often described by a mathematical tool known as a differential equation. And based on the control decisions of your components and the model of your system, then you can use these equations to obtain the future evolution of your system. Now, while you can do these for point-wise analyses of the system, where you have some unique estimate of its initial state, one thing that you might be concerned about is the evolution of the system over large sets of scenarios. And you would like to be able to reason about the correctness of your system for every point within that space. So now the problem becomes rigorously reasoning about the evolution of your system over sets of initial states, inputs, and even potential disturbances. The nuance here is that you're not discretizing these sets and then performing your analysis, but rather you're rigorously exploring the behavior of the system for every point contained within that set. Now, there's a rich set of literature and software tools available for the reachability analysis of many types of systems. And one of the key characteristics of these approaches is that it's often prohibitively difficult to obtain the exact reachable set for many classes of system models. So you customarily compute a sound over approximation of the set, such that the actual behavior of the system is contained within that larger over approximation. And there are many ways of representing that set. And depending on the type of representation you use, you can characterize the actual executions of your system more and more closely. The challenge here is that there's usually a trade-off between the fidelity of your reachable set computations and the time that it takes to compute them. So as an example, if you use a set-based representation called hyperrectangles to describe the evolution of these systems, then these computations can be done in real time. And in our work, we utilize this formulation to describe the autonomous platforms that we considered. And in this figure, we are showing a 2-second projection of a left turn action for a 1/10 scale autonomous vehicle. So the green rectangles here represents the set of states over this finite horizon, where this purple line is a simulation of a single point from the initial set that we considered. So now coming back to the original safety question, the reason that reachability analysis is so helpful is that you can pose the safety problem as ensuring that the reachable set of your vehicle that you're concerned about never intersects with the obstacles within its environment, as well as the set of reachable states of the dynamic environmental participants. And in this figure, ego represents the vehicle that we're concerned about, and its evolution is described by its reachable set shown here in blue. In like manner, the reachable set of the opponent vehicle is shown here in purple, while static obstacles are represented by these orange boxes. So the idea here is if you forecast the effects of these control decisions made by your system and identify when unsafe situations occur, then you can possibly switch to another controller that will get you out of trouble that we show here in red. So here I show an example of using this approach to assure the safety of a 1/10 scale autonomous platform that we utilized frequently within our experiments. And in the figure on the right, what is happening is that we're doing that projection, where every time in time, we're taking each of the control decisions projecting them forward in order to see if they intersect with obstacles within the environment. And anytime you see a green trajectory, the decision made by the system is safe. And anytime it turns red, then the current control action would lead to a potential collision if selected for the duration of the finite time horizon that you're reasoning about. So there are several assumptions that bear mentioning here. The first is that we have an assumption about the underlying dynamics of the car. And in this case, those were obtained using a process known as system identification, where you record the data of driving the vehicle in a diverse set of contexts, and then use those experiments to tailor a physics model to be able to describe its behavior. And in this case, we utilized a kinematic bicycle model, which is a particularly useful model for describing front steering vehicles. The second assumption is we assume we have an accurate method of measuring the position of static and dynamic obstacles, as well as the position of the vehicle, which requires an assumption of accurate sensor measurements. And the final assumption is that we assume that the control action used in the reachable set derivation is constant throughout their construction. So as mentioned earlier, one of the major challenges in autonomous applications is handling uncertainty. And since reachability regimes are inherently a model-based technique, the fidelity of our predictions is dependent on the strength of these models. And if they're not good representations of reality, then any safety declaration made through their use may be invalid. So as a brief introduction to these challenges, there are broadly three realms or sources of uncertainty within autonomous applications. The first is that the vehicle's understanding of the world is largely mediated by its sensors, and there are limits to the precision of the measurements of these sensors, which might also be affected by the type of environment that you're moving within. So it's important to allow for sensing uncertainty in your reachability computations. The second major headache is that it's quite challenging to characterize the behavior of dynamic agents within the environment precisely. And the models that we utilize to describe their behavior need to be able to capture this reality. And finally, the models that we use to describe the physical dynamics of the system is inherently an abstraction of reality. And capturing its behavior precisely is complicated due to the presence of phenomena that are hard to characterize explicitly, such as drag forces, friction forces, non-observable disturbances, and other stochastic elements. So within the research literature, these two sources of uncertainty can further be classified into two major domains. These classes are epistemic uncertainty and aleatoric uncertainty. So epistemic uncertainty refers to the uncertainty that is attributed to a lack of knowledge of the dynamics of the system and its environment. And it can be reduced by conducting more comprehensive experiments of the behavior of your system, or even using a more precise set of sensors to better understand the environment. Aleatoric uncertainty, however, refers to irreducible random uncertainty, and it is characterized by the variation of physical systems due to random effects. So within our context, an example of where aleatoric uncertainty would show up is in the models of the behavior of the dynamic agents within the environment. And while it's possible to come up with a probabilistic description of their behavior, in practice, the behavior of dynamic agents within the environment can be unpredictable. But the overall idea here is that if you can come up with an estimate of the variance of these parameters in different contexts, then what you can do is use reachability analysis to explore the behavior of your system over these large sets of scenarios and see if the system satisfied the required levels of consistency, robustness, and quality governed by the assumptions of these estimates. So let's now think about uncertainty in a principled way. Let's assume that we have a model of the underlying system. And since the experiments we've been talking about so far involve this 1/10 scale autonomous remote controlled car, let's assume that it can be described by a kinematic bicycle model, which is a decent model for describing a front steering vehicle moving at reasonable speeds. The dynamics here are represented by an XY position, a heading variable, and a variable describing the system's velocity. And while this model applies to many vehicles in practice, to get it to describe the F1/10 model precisely, we had to tune three parameters within this model, mostly around the vehicle's velocity profile, to be able to capture how the system's throttle commands affected its movement. And specifically, the parameters we had to determine were the acceleration constant, the hysteresis constant, and the motor constant governing its behavior. And as you can see below, we were able to obtain quite an accurate model using data collected from a large set of experiments. Now let's assume that we want to be able to describe the uncertainty in our estimates of the vehicle's state, such as its position or velocity. So for example, let's say that our estimations of the vehicle's position and velocity are only accurate to within plus or minus 10%. Then we can allow each of the variables in our model to be described by an interval, where an interval is a set-based representation of the ranges that these variables can take on. And in doing so, you can explore all the evolutions of your system for all position and velocity values within that range. By allowing the variables in your dynamics model to take on these set-based representations, we can now model the behavior of your system by what is known as a differential inclusion, which is a generalization of ordinary differential equations to describe set-based dynamics. But you can also handle the other sources of uncertainty, such as external environmental disturbances and the uncertainty in the specific parameters of the kinematic bicycle model in the same manner. So now let's look at how this looks in practice. So one of the things we considered in our experiments was modeling the uncertainty of determining the position of autonomous system, which is arguably one of the most difficult and fundamental parts of the entire process. So in a real autonomous system, estimations of the vehicle's position within the world must be accurate to within 10 centimeters or better, which has resulted in numerous methods proposed for solving this problem. So within this context, one of the most popular localization techniques are called particle filtering methods, which allow you to describe the vehicle's position using a probability distribution. So the idea here is the position of the vehicle can be represented by a large set of particles that describe our estimates of the vehicle's position and orientation. And typically there's a large number of these particles that converge around the vehicle, and they're refined using the measurements from its sensors as well as presupposed motion models. And one of the things you can do is explore the behavior of the system from all of these estimates to assess if your system is safe. And in the video below, you can see our experiments of allowing for such an analysis. So in doing so, you can be sure that any safety declaration made by your reachability approaches have incorporated this level of uncertainty in the localization of the system. So now beyond localization uncertainty, how would you deal with the uncertainty coming from the vehicle sensors, as well as the uncertainty with respect to the evolution of the agents tracked by these sensors? Well, you can approach the problem in a similar manner. So let's imagine for a moment that we have a sensor that allows us to track the position and velocity of dynamic agents within the environment. And let's assume that although our measurements of their position are quite accurate, we want to be able to account for the inherent unpredictability of their behavior in the models that we're using to describe them. Well, one thing you can do is take a conservative mindset and inflate each of your estimations of their state to explore larger ranges of behaviors in order to make sure that no collisions occur. Well, depending on the level of uncertainty that you consider in your estimates, the set of possible behaviors can grow quite quickly. So the cost now is that the set of unsafe behaviors issued by your system is quite large. And in these videos, what we show here are the reachable set of dynamic agents within the racing environment. And these green and red boxes are the reachable set of the ego vehicle. And as you can see, as you increase the uncertainty in the estimation of their position, the number of intersections detected by your approach increases significantly. And the same can be done in modeling the underlying uncertainty in your system models. And if you allow the parameters of your model to be described by intervals, such as the acceleration constant, for example, the hysteresis constant, and the motor constant, then you can reason about large sets of behaviors utilizing this approach. So a potential application of such an analysis is characterizing the behavior of your system operating on different road surfaces or even different weather conditions. So up to this point, we've been discussing how one would detect potential safety violations made by the controllers in a variety of contexts. But a crucial question that must be answered is what happens when a problem is discovered by a monitor, and how do you maintain safety within this context? And one of the most popular frameworks for satisfying both requirements is the simplex architecture. So the simplex architecture here is an architecture that is quite useful for switching between a high performance controller that maybe allows you to perform a series of really complex maneuvers, and another controller that may not be as performant, but you know will maintain safety. So let's imagine the system is making use of a controller, such as a vision-based neural network. They might work quite well in many settings, but sometimes produces bad predictions. Now, one thing you can do is use the reachability computations to detect when an unsafe decision has been made. And then you can transfer control from this neural network component to a controller that's been designed to optimize for safety. So a useful analogy of what we're doing here is a driving instructor's car with 2 sets of steering wheels and 2 sets of brakes. As long as the instructor is capable of intervening in dangerous situations, then the speculative student is allowed to drive. So if you put everything together, if you leverage the reachability approach for the detection of these potential safety violations, and then make use of this architecture to switch between a high performance controller and an underlying safety controller, then what you get is a method for assuring the safety of controllers within autonomous applications. And we evaluated this approach both in simulation and on an embedded hardware platform, using a diverse set of controllers in many environments. So in the videos of the screen, one of the examples we considered was assuring the safety of a vision-based machine learning controller that learned to map images captured from a frontward-facing camera to steering commands in order to move around this racetrack. And while this controller works pretty well in most contexts, if you change the configuration of the track or even change the lighting conditions a little bit, it can sometimes demonstrate erratic behavior, which you can see an example of in the image on the left. And sometimes this erratic behavior leads to collisions. And on the right, we were able to eliminate those collisions using the simplex architecture. The trade-off here is that you sacrifice some of the performance of your optimal controller for this slower moving safety controller. However, the benefit is you're able to eliminate these collisions. Now, if we return to our conversation about uncertainty, you can also include these analyses within this constant. And what you will find is as you increase the uncertainty in the underlying models used within your reachability computations, the use of the safety controller within the simplex architecture also increases quite significantly. Additionally, one of the things that you can be able to do is explore the limits of how these things scale as you increase the level of uncertainty in the underlying models. And we evaluated this with respect to two metrics. The first was the growth in the size of the reachable set as measured by the area of their projections. And the second was the percentage of the time that the safety controller was engaged during navigation. And as you can see, there's an exponential relationship between the growth of the reachable set and the amount of uncertainty that you consider in your models. The same is largely true of the use of the safety controller. However, the increase in this realm is much less straightforward. And while it also generally increases in an exponential fashion, its use is also highly dependent on the path that the vehicle selects while navigating through the environment, as well as its interaction with dynamic agents within the environment, which explains the non-smooth nature of these plots. And if you take this idea to its logical conclusion, if you also could increase the prediction horizon used in the reachability computations, then high levels of uncertainty can make these reachability predictions functionally unusable. So the plot here is an example of exploring the uncertainty in the acceleration constant, hysteresis constant, and motor constant defining the F1 tensor dynamics. And as you can see, there is a sub-exponential increase in the size of the reach set as you increase the reachability time horizon, and an exponential relationship between the growth in the size of the reachable set and parameter uncertainty. So sufficient care must be taken in system design in order to develop really high fidelity models with manageable levels of uncertainty. So to summarize what we've seen so far, we developed a reachability-based safety assurance framework for reasoning about the safety of systems in dynamic and uncertain environments. So in terms of future research, many autonomous systems make distributional assumptions about the environment, thus requiring the need for probabilistic modeling, particularly around the behavior of dynamic agents. So extending this approach to consider the use of these models would be an interesting study. And additionally, one of the assumptions that we made in our work was that the control action used in constructing the reachable set was constant throughout their derivation. And it would be interesting to explore the use of closed loop reachability techniques aimed at lowering the conservativeness of these resulting sets. And now for the second part of my talk, I'd like to take a little bit of a different perspective within autonomous systems development. So in the last project, we were concerned with making sure that the actions of these controllers did not lead the vehicle into unsafe situations. But one of the things that we didn't consider was the performance of these controllers at driving the vehicle within its environment. And the second part of my presentations deals with this latter objective. And how can you use reachability analysis to generate high performance controllers for autonomous systems? And specifically, the inspiration of this project really came from our participation in an international autonomous racing competition known as the F1 tensor. So it might sound a little counterintuitive to think about autonomous racing in the middle of a talk about safety assurance techniques for these systems. But one of the major motivations of considering the racing problem within research is that it allows you to consider problems such as high-speed obstacle avoidance and other high-risk maneuvers that may be too dangerous to consider in urban settings. And there have been several high-profile competitions over the years, such as the India Autonomous Racing Competition that occurred at CES earlier this year, where 9 teams from 21 universities were able to compete in a series of races involving full-scale Formula One racing cars at the Indianapolis Motor Speedway. And there have been several other smaller scale competitions occurring biannually at conference venues across the world, known as the F1 tensor. And one of the major challenges here is figuring how to deal with the aggressive and uncertain behaviors of opponent vehicles at high speeds. And as you can see from the GIFs on the screen, optimizing for speed while ensuring that you don't crash is not a straightforward endeavor. So fortunately, we've already seen how to handle the uncertainty in characterizing the behavior of dynamic agents within the environment. And building on that work, our idea is to design a controller that explicitly uses our estimation of their reachable sets to avoid entering situations where a collision is likely. And if we can avoid this set at all times, then we can have a reasonable guarantee that we'll be safe. So the question now remains, how do you generate these controllers to accomplish this task? So one of the most powerful methods for solving this problem is using a set of techniques that fall under the realm of a framework known as model predictive control. And this framework is an optimization-based method for determining the best set of control actions that allow you to perform some underlying task. So as an example, if your desire is to find the steering and throttle commands that allow you to follow the best racing line within the environment, then you can view this as generating the inputs that minimize the time needed to travel along that trajectory, as well as not deviating from that racing line very much. Now, one thing that might happen is that you simply follow this path at the maximum speed. But that's undesirable since the chance of spinning out is quite high. And you want to generate these inputs in a way that respects these constraints. So to do that, you have to ensure that the approach takes into account the physical dynamics of the vehicle, as well as constraints on the types of actions that it can take. For example, these can be limits as to how fast you turn or even accelerate. And with these constraints, then you can then ensure that the actions produced by this framework will be reasonable in nature. Now, one thing to note is that the search for these inputs is being done continuously as you move throughout the environment. And you're really only considering the best actions to take over a short time horizon. And this allows you to deal with the dynamic nature of the environment as well as the vehicle. So far what I've laid out is the classic setup of model predictive control. And what you can do is augment this framework to include constraints that are derived from your desire to avoid obstacles. And this can include the reachable set of opponent vehicles, as well as the static obstacles. And this is primarily what we looked at doing in this project. So the idea here is to limit the search space of the optimization problem to guarantee that the inputs generated by this method allow you to remain within a safe region of the state space. So while this seems relatively straightforward, one of the challenges of requiring the vehicle to assume positions outside of the location of obstacles is that it converts your search for the best control action into a non-convex optimization problem. But what does that mean? So the idea here behind a lot of optimization problems is that we're trying to minimize the value of some function that may capture, for example, the time needed to track a path throughout the environment. And if the function is convex, then finding the value that minimizes this function is relatively straightforward. And you can be sure that the answer you're given is indeed the best answer. But if the optimization is non-convex, then the problem is significantly harder and takes more complicated strategies to find the best inputs. And although some good solutions to this problem have been proposed recently, convex optimization approaches are generally far more efficient. So what we'd like to do is come up with a way of specifying our safety constraints in a way that allows us to generate these actions quite efficiently. So if we look at the existing literature within this space, there have been two main approaches to solving this problem. So the first camp of methods have entirely avoided specifying safety constraints as part of the MPC problem and handling them rather within the planning layer of the autonomy stack. So instead of generating control inputs that are guaranteed to be safe, you can instead synthesize a safe trajectory and then simply track it. A challenge here is there are many planning approaches don't reason about the underlying dynamics of the vehicle to a sufficient degree when planning, which can sometimes lead to behaviors that are less than optimal. And at the same time, many approaches cannot be executed fast enough online to deal with the high speed and aggressive behavior of other vehicles. And the second camp has really tried to formulate this problem into one that can be efficiently solved by only using linear constraints to encode the safety problem. So for example, a work by Alex Liniger and his colleagues, they were able to encode the problem of avoiding bad areas within the environment by limiting the area where the vehicle could traverse to lying within two parallel planes. And this allowed them to obtain a really high performance controller, but their approach didn't consider dynamic obstacles. So one of the challenges of limiting the planes to be parallel is that this approach may fail if a vehicle is directly in front of you. But in general, it's a really effective way of handling this problem. So building off their work, we explored altering their approach to be able to handle dynamic obstacles by letting these planes have different positions and slopes depending on the state of the vehicle. So this would allow you to handle the case where a dynamic obstacle is directly in front of you. And it would also allow you to increase the space of where the vehicle is allowed to navigate. Now, there's no requirement that you only use two planes. And in practice, you can use as many of these as you would like. However, one of the challenges here is that in order to determine their slope, you have to solve another optimization problem online that generates these planes. In most scenarios that we considered, 2 planes is sufficient. And if you use this formulation, then now you have a way of specifying your safety objections in an efficient manner. So now if we return to our original problem formulation, what we've effectively done is circumvented the need to encode the requirement of limiting our search space to be outside the space of obstacles, into deriving these 2 linear constraints represented as planes. And in doing so, the problem can now be efficiently solved by existing model predictive control tools. I'd like now to show you a demonstration of evaluating our approach in numerous contexts. And on the left, you can see the approach proposed by Alex Linegar and his colleagues, where these parallel lines are used to describe the safe region. And on the right is our extension of allowing the slope and position of these planes to be altered online based on sensor data and our reachability computations. So in this case, the red boxes are a set of dynamic obstacles whose evolution is only determined from the vehicle sensors. The blue rectangle is an opponent agent whose behavior is being described by our aforementioned reachability computations. And the magenta dot is a target point that we're trying to get to as we navigate through this environment. And this dot is synthesized by a couple of different planning techniques. So our evaluation was quite complex in the types of scenarios that we considered. And in practice, it was quite successful in dealing with the dynamic nature of these environments. So what are the challenges and limitations of these approaches? So as previously mentioned, one of the challenges with the parallel plane formulation is that it can fail when obstacles are directly in front of it. And avoiding collisions is highly dependent on the underlying local planner that is guiding the selection of a target point that MPC is optimizing to reach. And in some cases, these planes can actually lie on top of each other, resulting in no safe region to explore. And an example of this is shown on the video on the left. While our optimization-based plane avoids this problem, one of the challenges here is that the computation time needed to generate these planes increases significantly as you increase the number of obstacles within the environment. And the other challenge is that depending on the objective function that you use to specify how these planes are generated, this can take prohibitively long. But these functions allow you really to optimize for the space that your controller can select good action to take. So there's an inherent trade-off within this space. So as a summary, what we've seen here is a method for generating high-performance racing strategies through the use of reachability analysis and model predictive control. And there are a lot of exciting areas for future research. And one of the things that can be done is considering the application of these approaches on the F-110 vehicles. Additionally, there have been several other exciting methods for specifying safety constraints within optimal control problems. And several of these approaches would allow for an investigation to see if we can develop more and more effective racing strategies. So I'd like to conclude by saying that formal methods are a powerful mechanism for thinking about the correctness of these systems. And in this talk, we surveyed how a class of formal techniques involving reachability analysis can be used to handle the safety question in dynamic and uncertain environments. Moreover, we also touched on how reachability algorithms can be used to derive optimal controllers for autonomous racing. In terms of open research directions, there's still a lot of work to be done within this space, and I'd like to touch on a few interesting areas that are particularly exciting. The first is, so far, the work we've looked at has looked at the traditional formal methods problem, where the safety question for the system is treated as a yes or no answer. But many learning-based applications are specified in terms of objective functions, where a system is trying to optimize its behavior in terms of specifying its cost or rewards. Moreover, there can be multiple objectives, some of which must be satisfied together, and others that may need to be traded off against each other in certain environments. So a key question in this space is, what are the best ways to unify this yes-no formulation of formal methods and these quantitative approaches in reasoning about the correctness of these systems? Another active area of research is the consideration of systems that learn online. So frequently, these systems make use of machine learning methods such as reinforcement learning. But the key question here is, how do you adapt these formal approaches to these systems to either A, account for the future changes in the behavior of the system, or else be performed incrementally and online as the system evolves? And if online safety approaches are used, like the ones we've seen in this presentation, then how do you prevent the machine learning mechanisms from being overly reliant on these safety mechanisms, which is a key challenge within this space? And finally, so far, most of the methods that have been developed have proven very effective at generating examples of errant behavior and learning-enabled systems. But a key question arises in how do you use formal methods to systematically select, design, and augment the data used in training these systems. Intuitively, once you've identified a problematic model, how do you then fix that model so that it performs well on the task that it's been selected to perform? And there's a lot of exciting work within this realm. And I'm excited to explore these approaches in my future research. So with that, before I move into questions, I'd like to acknowledge some really important people who made all of this work possible. So first, the people who funded my research. I'm very grateful to them for the ability to have done my research over the last couple of years, and in particular, the DARPA Assured Autonomy project that I've been involved with during my time here at Penn. Next, I'd like to start by thanking my committee members. Thank you for taking the time today. I know that this is a particularly busy time of the year. So thank you to Professor Gabor Karzai, Stanley Beck, Janos Stepanovic, Alan Peters, and Dr. Johnson. I'd like to especially thank Dr. Johnson for seeing the potential in me when I stumbled into your lab in 2017. Couldn't have asked for a better advisor. Thank you for creating a space where all of us could thrive and express our creativity, as well as the guidance and opportunities that you provided along the way. Greatly appreciate it. Next, I'd like to thank all the people that I've had the honor of working with over the last couple of years. And I'll start with my members of my lab. It's a pleasure to work with such a kind and hardworking group of people. So thank you to Xiaodong, Nilanjana, Preston, Tianshu, and Ayana. Nate and Diego, I can't thank you guys enough. We've worked on so many things together and experienced so many things as well. Couldn't have asked for better friends and colleagues as we figured out this whole graduate school thing together. I'd also like to thank Tran for his generosity when I started out at the beginning, for all the time you spent helping me figure out how to do research. You were an incredible mentor and a role model in my life. I'd like to give a special shout out to Nog for the Zoom calls and sessions we spent together, improving so many of the projects that we spoke about today. I know my work would not be what it is without you, so thank you very much. I'd also like to thank Shreyas, Tim Dara, Paulius, Brad Pottinger for being some of the best collaborators and friends as well. And finally, I'd like to thank the Open Robotics folks that I got to work with last summer for an incredible experience. I'd like to give a special shout out to Kat for being an awesome mentor, Michael Carroll, and Michael Geronimo as well. And I'd also like to thank Adisu for the kindness along the way. I think yours was the first dissertation defense I ever attended, so thank you for showing me the way. And now I'd like to take some time to thank my community both here and in Nashville and around the world who really made this journey possible. So I'd like to start with Kayula, Brooks, Ketis, and Augustus, who are the community that I found when I first moved to the States in 2013, and have continued to be a big part of my life to this day. Appreciate all of you, and you inspire me every day. I'd like to thank Thomas Tranquil and Joseph Mujisha for all the mornings and late nights we spent working together on Zoom, the many FaceTimes, and the random trips. Thank you all for giving me life on so many occasions. Thank you to Erskine for so many random adventures. I don't know how you never get tired. Thank you. I want to give a huge shout out to the Enclave crew for not only helping me with my research, but for the ridiculous amount of food and fun that we had as well. To Brian Ondeng, Durango, and Chalo, thank you boys for always seeing the best in me and for so many good conversations. To my Nashville rugby family, thank you for being one of the first communities that I plugged into when I first moved here. I know there are many of you on this call. I appreciate you all, and I promise I'll be back out of practice. I'd like to thank Dina for being one of the most supportive mentors over the last couple of years. I can't thank you enough. Dina, you were there on the day I graduated with my master's, and I can't tell you how much that meant to me. The same is true for Mike Bryant. Thank you for the many meals over the last year and for the knowledge and belief that you extended me as well. To my roommates, Joe, Inger, Alberto, Shannon, Michael, and Nick, COVID was a wild adventure, but if I had to choose a set of people to do lockdown with again, it would always be you guys. So I appreciate and love all of you. And sometimes you stumble into groups of people who make you feel instantly at home. So to the African community here at Vanderbilt, thank you all. You all are incredible. And finally, to my family at the Black Codes, Trevor, Calvin, Dr. T, Glenn, Kanisha, Jamaica, Latavia, and Rob, and Curtis, you all inspire me every day. I'm thankful that I found you guys during my time here in Vanderbilt. And finally, I'd like to thank my family. I don't know where to begin. Thank you for the support, the belief, the calls, and all the love that made this possible. Many of our photos are at the airport, but thank you for making me feel close, even when I was 8,000 miles away. Thank you, and this one's for you. And there's so many other people that I want to thank, and you know who you are, so please accept my thanks. So let this day be a reflection of the power of community. And with that, let's go right into questions.
Great. Thanks, Patrick. Yeah, we can open it up for questions from anybody. A great job.
Hi, Patrick. Great talk. Thanks for this. I posted some questions in the chat in case the audio breaks up. But the first part was talking about this online reachability analysis using for differential inclusions. Was this something that you developed, or were you using just building off of existing tools in that area?
Yeah. So this was building off RT Reach, which was some previous work proposed at HSCC a couple years ago. But essentially, my previous work didn't really leverage the differential inclusion formulation of that tool. But in these projects, I actually allowed each of the dynamics to be described by intervals.
Okay, great. Thanks. And then the second part was you had mentioned that there was this constant control input assumption when you were computing the reach sets, right? So if there's initial state uncertainty and the neural network is outputting the command, wouldn't there be a set of possible commands that need to be considered for this? Or how did you get around that problem?
So you can you can allow the input to also be uncertain, since that input is being used within the underlying dynamics model as well. But one of the things we saw is that if you combine a large set of uncertainty, then the reachable set predictions become functionally unusable. So the analysis that I presented during the presentation was analyzing a specific piece of uncertainty at a time. But for example, you could also enclose the uncertainty within these predictions as well.
I see. So then would the proposed method be like you'd apply some neural network verification method for given an initial state, what are the possible commands being output? And then once you have that, you could use that with the reachability analysis.
Yeah.
Nice. Okay, great. Thank you.
Hey, Patrick. Great talk. Just have a quick question. You guys are dealing with a lot of uncertainty. Have you guys looked at trying to estimate the level of uncertainty using Bayesian models?
So yeah, that's a good question. There's a lot of different techniques that can be used to do this uncertainty quantification. So for example, you can use sensitivity analysis, or you can come up with these Bayesian estimates of how each of these parameters would perform.
Right.
We didn't specifically look at that, but that's definitely something that can be done. And based on those analyses, then you can then use those intervals to do this prediction. But in this work, we didn't actually do that. But that's an important question.
Awesome. Thanks. Great talk again.
Wonderful work, Patrick. Really very impressive. What Stanley and Brooks asked is kind of related to my question too. In part one, you looked at intervals of parameters, right, to determine where the reachability would be. Now, is that equivalent to using a uniform probability distribution over those parameters?
I would not say yes. I'd say in this case, those intervals don't really have a probabilistic interpretation. If you did use a uniform distribution, maybe they can, but within our work, we didn't assume that. Those are just based on your assumptions of the upper and lower bands of the variation of those parameters.
Right. So what would happen to that analysis if you did assume a probability distribution, a uniform one, or one that has one or more modes in it, or even a particle filter based thing? How do you think that would alter that first part of your system?
So I think, like, if you're describing the variance of a parameter by uniform distribution, so that isn't inherently kind of a type of range, right? So if you, in our encoding, we're actually exploring the evolution of your system for every possible variation within that range. So I don't think much would change here with respect to
not with the uniform, but what if you knew that some of the parameters were more likely than others and you represented them with probability distributions?
That's an interesting question. I think my current answer is I'm not sure, but that's something I definitely look at in future research.
Yeah, it would be worth looking at, because it may be that if you simply replace the intervals with probability distributions, you might actually be able to follow the same math through, but might come to different conclusions. I'm not sure. And of course, you could always use a Bayes filter kind of approach where you update you use a posterior probability to update a prior probability, compute likelihoods, and then compute where you would go based on that. I think that would be a very interesting extension to this, and it's in line with what both Stanley and Brooks were asking.
Yeah, definitely.
One other thing. Was chapter 5 a paper that you published?
Is chapter 5 the extension, the challenges and limitations?
No, let me see which one. What was it entitled? I just wrote down the chapter name, because, well, in at least one of them, you pointed that the chapter was about, came from a paper basically. In this one, you didn't, but in the chapter itself, you referred to this paper. So I was kind of curious if that was published, and if it was, then it's just an oversight on your part to not put that there. The other comment I have, I mean, this is very complete. It's really good. Extremely well written, but I noticed there's an awful lot of redundancy in your descriptions. A lot of things are repeated. That's actually not an issue for me, because sometimes, it makes it easier to refer to other things, but it also made me wonder about the pre-publication of some of this stuff. You need to be very specific, I think, in your dissertation as to what material you are presenting that has been presented or published elsewhere,
So I think chapter 5 there was a journal extension. So the prior work was published at ICAA earlier this year. And then this latter work where we did this uncertainty quantification was published, is being submitted for review at the Journal of Artificial Intelligence. So a lot of
I think it'd be worthwhile just to put a footnote on that page, maybe a little asterisk, and then down below, and say where the material was presented.
Yeah, definitely.
Good work, man. Thanks
Thank
for
you.
having me on your committee.
I appreciate it.
Okay, so I know Tran has a question, but Janos, I know you need to run, right? Did you have any question?
That's just great work, Patrick. So it congratulations to a very resultful PhD period for your in your work. So just one question: when you do this reachability analysis, can you tell something about how trustworthy is your reachability analysis, and what does it depend on? I mean, the trustworthiness. So did you do any kind of analysis, how much your analysis depends on some kind of a priori knowledge, what you assume about the nature of the dynamics, or any other kind of things? So because obviously this is for safety critical systems, and when you claim that I run a real-time reachability analysis, and until you build your control strategy that you listen to my reachability predictions, you are good. But how much should I believe that?
That's a good question. I think the strength of any of these predictions is based on the models you're using. So a lot of it started from first principles in how well does your model actually characterize the system you're analyzing. So we did a lot of experiments in doing model validation, conducting a lot of experiments of allowing the vehicle to be driven a lot of context and seeing how those models work in practice. But the other thing was, just even from a different perspective, was how many experiments could we use this approach and see how many collisions occurred. So what we ended up doing was conducting about 2 weeks worth of experiments of allowing this vehicle to traverse within these environments, and then seeing how many collisions actually occurred. And if you take a large enough set of these examples, then you can have an estimate of like the efficacy of your reachability predictions. So if no collisions occur over a large set of experiments, then you can have some level of confidence in it. But I think the fundamental assumption is that all these reachability computations are still a model-based technique. So while that can give you like a pretty strong guarantee that your system will operate correctly, perfect safety is something that we can't achieve.
Okay, thank you very much. Good answer.
Thank you, Jonas.
Okay, Tran, I think you're next.
Thanks, Patrick, for your great talk. I really enjoyed it. So I have two questions. The first question is about, can you explain a little bit more on how to use particle future and reachability analysis together?
Yeah, sure. Let me see if I can go back to that slide. 1 second. All right. So one of the things is like a particle filtering approaches allow you to like characterize the position and orientation of your vehicle using a large set of particles. So the more particles you use, the better estimation you have of where the vehicle is, right? So each of these is like described by an X, Y, a heading angle, and a different velocity, right? But what you can do is take each one of those particles and compute the maximum and minimum variation within your XY position, your orientation, for example. And if you allow for that type of analysis, then what you have now is a box or a set of initial pose estimations. So then using this initial set, you can do your reachability predictions. So the idea here is if your estimation of the vehicle state isn't a unique estimate, but is rather a set of estimates, and you can explore the evolution of all of them using reachability analysis. And that's kind of what we did here.
Okay, yeah, thank you. So my second question is, you say about your future research about quantitative guarantees for the safety. Can you expand a little bit more, like what type of techniques you think is going to work for that? That's what you want.
Yeah, I think that's an interesting question. One of the things is like all of the predictions we did basically said whether or not we're going to intersect with obstacles within the environment. But another question that you might ask that might be interesting to answer is, okay, if we're safe, by how much are we being safe? So one of the things is, how do you use these reachability computations to come up with those estimates? The other thing is, like, if you're considering this, for example, within, let me see, 1 second. For example, if you're using it within like a mission planning framework, where you have to balance safety along these higher level objectives, or maybe tracking a pipe, for example, one of the things that you might be interested in answering is, okay, I'm safe, but did I actually accomplish my task? So how that would be done, I'm not exactly sure. There's like weighted ways you can do that. There's various ways you can do that in terms of objective functions, but the specifics is something that I'm actually interested in learning. I'm not exactly sure how that would work.
Okay, thanks. Yeah, thanks for the answer. I'm interested in that problem as well. Yeah, I have solution for that. I just wonder, like, if you have any additional idea about solving that problem.
I'd like to talk after this.
Yeah, we can talk more about that later. Thanks and congratulations.
Thank you.
Okay, let's see, committee-wise, Gabor, any question?
Yeah, so this is my my hobby horse. What do you think about the real-time execution of these calculations? So timing, how this influences the decision making. I understand that everything worked out well in the experiments. You mentioned somewhere that on the TX2, when you tried to execute it, it was missing just a few deadlines. But in a safety critical systems, you often have to always meet the deadlines. So how would this work in a safety critical environment, which is also timing critical?
Yeah, I think that's a good question. With respect to all the experiments that we conducted here, we didn't really leverage any real-time operating systems. So specifying the deadlines for each of the computations that need to be executed wasn't possible. So you're really just relying on the underlying operating system. But if you're going to do this in a safety critical system, you definitely need to use a real-time operating system. But with respect to the reachability algorithm, it's been designed in a way that it doesn't need dynamic allocation and can be run within these environments quite well. So one of the things that just can be considered is how would you use this within a real-time operating system? So.
Okay, that's good. Thank you.
Yeah, and I think you have a table with all this too. I don't know if you have it in the slides, but we did characterize this.
We did. I don't think I have them in this presentation.
Okay, it's in the dissertation though, and in one of the papers. Because yeah, this is important, right? It's the evidence for this, and this is an important constraint. Okay, any last audience questions? Okay, I'll ask a high level question, I guess, and then what we can do, I looked into it a little bit. I think I can probably put everyone in like a waiting room or something, something like that. And I think the committee has asked most questions already, but so you talked some about it, but and I know, you know, you're finishing your PhD, but you know, if so, what would you give someone who is starting a PhD in this kind of area? What project do you think you would give them? So you talked some about future work, but you know, what would your suggestion be?
I think the verifiable training and data generation stuff is probably what I would give as a project for someone. I think it's very interesting within the last years that we've come up with a lot of techniques that allow you to demonstrate when these systems aren't performing well, but coming up with ways that you can also generate data that makes the system better based on how these systems are performing would probably be interesting. Like as a concrete problem, then probably just looking at closed loop reachability analysis for these systems. It's a little bit difficult when you're considering perception models, but that would be an interesting one. So those are probably the two projects that I would focus on.
Okay, great. Any last questions for the committee? Do we want to have a session with just us and Patrick, or do we just want to move directly to our discussion?
I do have one question for you, but it certainly can be asked in public here. What do you intend to do next? What are you going to do after this?
So I'm going to go work in industry. I'm going to work at Google as a cloud optimization engineer. So it'll be a mix of how do you optimize machine learning models for the cloud, but also how do you also ensure that they are operating correctly. So a little bit of it will be involving some of the stuff that I've worked specifically here.
Are you going to, where is it, Palo Alto, Santa Clara, somewhere? Where is that?
So I'm going to the Research Triangle. I'll be in Raleigh, the Raleigh-Durham area. So
okay, cool. That won't be maybe quite as expensive, and the traffic probably won't be quite as bad. But that's great. That's great. Many congratulations.
Thank you so much, Dr. Peters.
Okay.
Something went wrong. Try again in a few seconds.
Oops, good. Okay, so let me try to figure this out so we can have the committee discussion. Give me just a sec. I'll try to not kick everyone off. Okay, yeah, I don't know if that's gonna work because I can do a breakout, but then if I try to do waiting room, I've got to do it one by one. Yeah, so if I'm open to suggestions though, we could do a breakout and I can do that, but otherwise we may just want everyone to drop off. Any preference or suggestion?
I think that if everybody else that's not on the committee or Patrick goes away, that would make sense.
Yeah, then I can just put Patrick in the waiting room. So yeah, so if you aren't on the committee, thank you for coming. Sorry, it'll be a little anticlimactic at that point, but we can give Patrick our congratulations, I'm sure. Okay, thanks everyone. But committees stay on and then we'll put Patrick in a waiting room in just a minute. This would be normally where we asked to kind of go out of the room. Okay, almost. I'm going to remove a couple people manually just in case they had stepped away or something. Okay. All right. So I think we have just the committee and Patrick. Any confidential question?
Not for me.
Okay, good. All right, Patrick, I'll put you, I'll put both of you in a waiting room, I guess.
I'll just leave with the other one.
Okay, okay.
1 second.
Okay, and then this one, let me see. You have to make me full host, I guess. I can't be co-host to put you in a waiting room.
Let me make host. There you go. Should be host now.
Okay. Okay, right. We'll bring you back in a minute.
Sounds good.
Okay.
Are we still recording?
I'll stop the recording.